Hello, this video will present how we can easily optimize a secant pile wall supported with tie-backs. We'll create a 30-foot excavation with a secant pile wall and a single level of tie-backs, and we'll optimize this quite quickly. First of all, we'll have the model. We'll double click on the wall. We'll click Edit Section. We'll select the secant pile wall with steel beams. There's different secant pile wall options. This will constitute the soil mix wall. We'll select the 2.5 foot diameter and space the piles at 4 feet on center. We can start with a section at W18 by 175. We won't change the spacings of the pile, so we'll keep everything the same. We can go to draw and look at what our wall looks like. We'll start off with an initial wall length of 50 feet and we'll progressively build our model. So we'll go add stage, excavate 10 feet by dragging on the surface. You can also change the elevation here by typing -10. We'll add a right click, add a new stage, and here we'll draw a ground anchor. We'll first click on the wall, then click on the ground surface. We'll change the elevation to -8, the inclination to 20 degrees, free length to 30, fixed length to 25. Let's put an 8-foot spacing. And we'll put a pre-stress here just to start off with. That can only affect the nonlinear analysis 70 kips, but we can always change that. Now we can double click here and also change the soil profile. So at -15 we're going to put another soil layer which we're going to call S1. We can edit here on the soil properties. We have it as a sand, silt we'll put as a sand. We have a total unit weight below the water table, dry above the water table, an effective cohesion, effective friction angle, elastoplastic properties for the nonlinear analysis, although this will be done later, and an ultimate bond resistance for the tiebacks. Let's put 30 psi here. Now this depends also on the soil type and your construction methodology, but you can always pick up values based on various recommendations. We'll right click, add another stage, and we can go in here and type -30 on the elevation. Take also down the water table, so let's do some extra dewatering and say we're going to be dewatering this to -35 so we can keep a dry excavation. We can also go and draw a construction load, draw surface strip search, select one point on the ground surface, select another one, set the coordinates, name this construction load, .6 KSF, 600 pounds per square foot, surface load. Now you can right click on anything, deactivate, right click, activate. Same thing with the tiebacks, right click, activate and deactivate. Now it is important to go in the analysis tab and switch the analysis to limit equilibrium. So this way our optimization for the wall embedment can take place automatically. In the nonlinear analysis, the program will not automatically optimize the wall embedment because there are soil interaction effects, soil structure interaction. If you had clays, we could change between drained and undrained. We could also do a full flow net analysis, although right now we're doing a simplified flow. Now since we have a stage where we have at least one support, we'll select the FHWA apparent earth pressure method. We can click inside so we have further options. But we can see basically our design assumptions here. We'll go on design. We'll make sure we use US allowable settings. We have US members. We'll optimize the wall embedment. We'll target a safety factor of 1.3 for a temporary construction. Of course, you can change on the design tab what that requirement safety factor. This DL is an increment on the wall length. And with that, we're basically ready to analyze this excavation. We press the calculator button, and we're seeing that what the expected displacement is, the wall moments per foot of wall per beam. We're seeing that the structural ratio is quite conservative, and we're also seeing that's on the walls, on the moment capacities, and we're also seeing that we're overstressing the tiebacks in terms of the pull-out length. This is a stress ratio here. We can go on one design section and see these results on every stage and see where the reds are. Also, the program has optimized the length of the pile, and now we have a 12-foot length here for the wall embedment. Of course, there are some other aspects that you have to take a look at, but here what's critical really is because we are dewatering, we're obtaining a much smaller safety factor. Not smaller safety factor, but we're obtaining adequate safety factors at smaller wall embedment. If we were not to dewater, that will be a different case. So once we have established this, we can actually go and say optimize, and we can optimize the whole design section. So we can say optimize design section. We'll have to wait a few minutes while the program is checking to optimize the tieback length, this tieback section, as well as the wall section. Now what we're seeing here on the screen is the moment diagram, the support reaction, and the red line here is the design capacity. You can actually move your mouse on top of it when the program is active and not doing the optimization as it's doing right now, and you can track any value at any elevation. So now that the program has actually come back and it's saying, look, you may use a W21 by 50, and you could go as low as you could use different sections depending on what you want, and these are your savings. So let's say we don't want to go that low because also our displacements are being affected. We could select a W24 by 55. Also, our strands are being optimized. So initially we had 4 strands, the optimized is 6, and now the program also optimized the tieback length. So we can rerun this analysis, but just to make sure, we take out the optimization. We will probably double click on the wall and just make sure that we round this to 42 feet. Press to calculate and make sure that everything, our stress checks are fine. We will look at the displacements and so on. And also on our tieback, everything appears to be fine. With the moments on the wall that we can track, the horizontal soil pressures, the net horizontal load on the wall, water pressures, and surcharge pressures. Now we could go on slope and select to perform a global stability analysis. Now this is a circular option, Morgenstern price, and we can see a global stability circle if we wanted to. Additionally, we could go to optimize, select to calculate the project cost, go to cost estimations, select our location. Let's select New York for this example. The program picks up the cost installation factors. There's different inputs here that you could change for tiebacks, walls, struts, in terms of installation and material costs. You can go use overhead and profit, specify the length of wall perimeter, of bracing, and of excavation perimeter. And calculate the whole project again. And go back on the results, on the cost summary, and get a project estimate for the costs based on what we have defined, as well as a detailed quantity takeoff. Now, a full quantity takeoff can also be done with a 3D model, but this is is covered in other videos. Thank you for watching this video. Please let us know if you have any questions. We'll be more than happy to help you with them.